We have a yeah, no, you can stand. Okay.
What's up?
We're saying how pretty it looks.
Yeah, this is summertime.
Oh, okay.
You definitely come visit in the summer.
So our next speaker is James Rondinelli from Northwestern. We'll talk about rational as opposed to irrational.
Bottles, yeah, for forward.
Thank you for coming.
Yeah, no problem. So thank you for the invitation. I am a material scientist, so JP had us self-identify yesterday, and I think most people were physicists or chemists. There was only a handful of material scientists. And even worse than that, I'm a computational material physicist. So like Raphael and Karen here, we don't actually make experiments in the lab. But what I'm going to try to tell you, which I think is very useful for experimentalists, is to understand how we think about building models for both forward design and inverse design. And I'm coming from Northwestern, as I mentioned, in the material science and engineering department, where we work on a lot of topics. One of those is quantum materials. If you're interested in other research we might be doing, you can scan that QR code and get to my website. JP also told us yesterday that quantum materials originated here from the study of correlated materials. So I've tried to juxtapose correlated materials, at least how I understand it, from quantum materials. And there are many challenges that we as researchers, either scientists or engineers, are interested in overcoming. In correlated materials, it's understanding complexity of strong correlations, understanding emergent phenomena, understanding disorder and inhomogeneities in materials. And then quantum materials, we've heard many ideas about topology, understanding criticality, entanglement and decoherence. And this hasn't been discussed here, but this is very relevant in quantum sensing, quantum computing, which is an area of research I also work on. I am in the materials science and engineering department. And much of this meeting or this workshop school is focused on understanding material synthesis and quality and measurement and characterization. Maybe not so much the engineering, but we'll get there maybe in a future winter school. What I'm going to try to tell you about is this bit here, understanding emergent phenomena, really computational materials design, my perspective, and how we think about designing new materials. We had a nice presentation earlier by Leslie about how she thinks about selecting interesting materials for study. And I'll tell you how we're thinking about that as well. This will apply both to correlated materials as well as quantum materials. And so today I missed my own class yesterday, so today I'm lecturing for you. And these are the learning outcomes. So as an instructor, the way we design courses is by thinking about what you should be able to do after this lecture. And these are the things you should be able to do after the next, I've basically made 50 minutes of content, so you have 10 minutes of questions. I want to differentiate theories, modeling, and simulation. Especially in the materials community, we use these words interchangeably, but they mean very different things. Okay, I want you to understand what is the utility of a model, and a model mimics reality. It's not intended to capture everything. Okay, and if there's something wrong with your model, it's either a numerical issue or perhaps you're missing some fundamental physics in the model. Then I'm going to contrast forward and inverse materials design. So this is ubiquitous in the materials community. It's spilled over into both physics and chemistry. And we'll see what that difference is. Okay, what does it mean to do forward design? Really the focus of this talk will be inverse design. And I'm going to introduce a concept that's called systems charts, which we use in material science to understand how you go from processing a material, it could be the shake and bake method, it could be single crystal growth, all the way to understanding the performance of that material in some deployed device, some system, or some piece of technology. And this systems chart is going to be highly interconnected. And one of the main things we want to do as quantum material scientists is think about those structure property links. This is something Leslie also touched on. To do that, I'll mention briefly some of the degrees of freedom you want to be thinking about when designing your quantum material. So what's accessible, what can I tune? We're sitting in a chemistry lecture hall, so we'll use this periodic table that's up here, which is quite nice, throughout the lecture. And I'm gonna have you apply this systems chart to two examples. One will be to design a compound that undergoes a metal insulator transition. So a first order phase transition where there's a change in the resistivity of that material, and it'll be driven by temperature. That'll be the first example. We'll use everything we covered in the first part of the talk to do that. And then, germane to this workshop, we will try to design an ultramagnet, okay, from first principles. So I'll show you how to do that. And we had a nice presentation yesterday from Raphael about the symmetry constraints that will enable this design ultimately. So that's the plan. So let's jump in. A theory is an attempt to find a fundamental description of a physical process. It's a coherent group of general propositions used as principles of explanation for a class of phenomena. So that's a theory. A model, on the other hand, is going to be an idealization of real behavior. It's some approximate description that's going to be based on empirical understanding or some physical intuition about a system, okay? Models attempt to mimic reality to some level of accuracy. It's not intended to be a fundamental description that is strictly true, and models have various representations or simplifications. And a good example here is a map from Google Maps. So this is a satellite image. So this is the city of Chicago, this is the metropolitan area, and this is Lake Michigan. And what I put on top of that map is the transit routes. And this is reality. This is an image from space. Okay, this is what this looks like. Now, if we want to construct a model, we can simplify this reality. And this is a version from Google Maps. Again, if I just turn off the satellite imagery, but I maintain the transit map on it. And then I can go to the Chicago Transit Authority and get their version of the transit map, which is a further simplification of the train system there. So these are all useful, right, to different levels or different degrees. And the question is, what do I want to do with it? You know, this has the full reality. These are simplifications. And the model will then allow you to think about, you know, either is there some new physics I can get in a physical situation, or can I design a material? So in this case, we're going to focus on physics-driven models rather than data-driven models. And we heard a little bit earlier from Leslie about some challenges that data-driven models can have. They are, though, quite useful. And if you're interested in some data-driven models, which I think are useful, this is one from our group. I won't spend any time on describing it, but it combines Bayesian optimization with latent variable Gaussian processes to do the chemical selection that Leslie mentioned, you know, a chemist would rationally do by going up and down or left and right on the periodic table. This automates that type of selection. So there are folks trying to embed physics information or chemistry information into machine learning. And I think that's the way forward. So those are theories and models. Now simulations, on the other hand, are going to be a study of the dynamical response to a system. And typically, we have some piece of scientific code that numerically evaluates a model that cannot be solved analytically. So there's going to be some algorithm, and there's going to be some approximations that will go into that simulation to capture the physics. Prior to simulations, you know, what we did is basically use approximations, the ideal gas law, harmonic crystals, and so on. Now, these simulations cannot be separated from the underlying models. The simulations are going to be that dynamical response for a model, which again is mimicking reality to some level of approximation. So the simulations do not mimic reality, but mimic a model of reality, okay? So, you know, if a simulation doesn't reproduce what you see in an experiment, the experiment is reality, it is the trump card. It means there's something wrong with the model that you're looking at. Either it's too simple, it's incorrect, there's something missing, or the numerical implementation might be incorrect. And so for today's presentation, what I'm going to tell you about, again, is both forward and inverse modeling of materials. And the approach that I'm describing is not original to me. It was written down, at least as far as I can find, first by Mike Ashby, who some of you may know from Ashby diagrams, which plot property correlations against each other. And they're typically used in the materials community for material selection. So choosing a material for a given application. And this is the algorithm, approximate algorithm that we'll use to design some of these quantum materials. The other thing I want to point out, which has been known for a long time, but only really in the last decade or so been really implemented in practice, is that simulations provide a bridge between theory, models, and experimentation. So in this diagram on the left, which I've adopted from the Allen textbook here, you can see that if you look at the left column, we have real materials. On the right-hand side, we have model materials. And we're building models of real materials to some level of approximation. So we want to develop simplified theories. We let the models work out. There's some theoretical prediction. Experiments are made. And we try to compare throughout this process. Okay, this has been around now for decades. And what you see today is more amplified versions of that, where you have many cyclical iterations. This is a diagram I've created for a similar process for how we go from discovery of materials, maybe synthesis in experiment, to understanding how to characterize those materials and modeling them with simulation. And there's many loops here, as Leslie mentioned earlier, so we want to try to iterate on the development of new materials. So that iterative process often leads to optimization, which then takes us out of fundamental science into an engineering realm. So we've sort of abandoned then, the focus on the physical understanding. The other thing I want to point out, which you may have seen before when building microscopic models, is that they will all necessarily fall short of some of the realities we have in experiment. And this is a nice quote from George Fox, the statistician, that all models are wrong, but some are useful. So keep that in mind. Again, there's going to always be some nuance that's not captured completely by the model. You maybe only need it to be correct within 10%, 5%, 30%, or so on. So keep that in mind. Okay, so let's start to try to build some models. Maybe before I do that, I can ask if there's any questions. So that's a little bit of the primer on simulation, theory, and modeling. And this flow diagram, which is highly complex on the right, is taken from that Ashby paper. So this is the diagram he has on the right. On the left, I've simplified it with PowerPoint, and we're going to walk through all of those steps, or at least some of those steps, for the design of a new set of quantum materials. The ones we're going to focus on are shown here. We're going to think about, what is the problem we're interested in modeling. We're going to focus on identifying the desired inputs and outputs. So this is useful for a computational scientist, but as an experimentalist, you want to think about what experiment should I do in the lab. You have to have a hypothesis. How am I going to test that hypothesis? What are the independent variables I can change? And will that experiment actually allow me to answer the hypothesis or validate the hypothesis I've created? So you can work through this in the lab as well. And it's linearized, in a nice sequential order. And I recognize that experiments may not be linearized like this, but this will help you think about organizing, your own research. So we'll identify physical mechanisms of interest. Again, we're going to focus on metal insulator transitions and then ultramagnetism, and then how we interrogate the model. We can change or perturb essentially the structure. So before we do that, the other thing I want to mention is that there's a length scale issue that we need to think about. So when you're building the models, you can build models starting at the electronic structure scale, going all the way up to the mesoscale. But there's also the systems level component, and this is where we'll find utility in the systems chart. On the left-hand side, really, I think this is what this audience is interested in. It's actually the design of the material, the actual material. On the right-hand side, this is more the engineering application. This is design with the material. So once we've actually identified a material of use. And the way we go through this continuum of length scales, there's also time scales associated with the phenomenon and properties, is through this paradigm in material science, which you may or may not have seen. But this is really what separates material scientists from physicists, applied chemists, applied physicists, and so on, is this diagram on the top, which was taken from a science paper from Greg Olson, a former colleague in our department, where he tries to connect processing, structure, property, and performance relationships. And for the inverse design of materials, we're actually going from the right to the left in this set of chains or links in this chain. So we're trying to say, okay, there's a given performance I want. What is the structure that gives me that? And then how do I make the material to have that structure? Okay. So to put that in a more simplified way, we're going to use this Venn diagram of processing, structure, properties, and performance to think about both forward and inverse design. Processing is the way the material is made. Structure is the way the material is organized. Relevant to us here, that can be structure at the atomic scale. We've heard a lot about crystal structures. Is the material ordered? Is it disordered? But if you're interested in transport, we also have to think about structure at the micrometer length scale. So do I have grain boundaries? Do I have twin domains, et cetera? So we have to ask the question, am I designing the material at the atomic scale? Am I designing it at the microstructural scale, or so on? Properties, straightforward, this is the way the material behaves. And then performance, how well does the material do what it's intended to do in a given application? So for the inverse modeling, we're thinking about mostly materials design and discovery. And the idea would be to maximize a property such that the structure follows some constraints. That would be the inverse modeling approach. And the forward modeling is the property prediction. So we're going to try to describe some way in which the property that we observe or compute is going to be a function of or a functional of some sets of constraints, conditions like that. Okay. If you're interested in the slides, please just email me. I don't know if we'll make them available, but you can generally have all of these slides. So again, going from performance to processing, we're thinking about inverse modeling. Going from processing to performance, once we have a given structure, we just want to predict the physical properties. So let me linearize that. So this is the same diagram, but just in a block format on a PowerPoint slide. And what we're going to do is try to create a systems chart. So what we need to think about is this material is actually a complex system with many interacting degrees of freedom. It could be single phase, it could be multi-phase, or I can take a complex engineered system and write the systems chart. And what I'm going to do is show that this processing structure property performance is going to be some sequential set of actions. And what I'm going to think about is what actually goes into the processing, the structure, the properties, or performance of a given system of interest that I want to optimize. And I'm going to try to draw links that take me from structure to properties or from properties to performance in a given material. So this seems a little bit abstract. And so instead of jumping into a quantum material, we're going to jump into a very simple diagram for this piece of chocolate cake. Okay? So I don't know how many people have watched this FX show, The Bear. Has anyone watched The Bear? Okay, some of you have. This is somewhat about, there's no spoilers here. This is about a restaurant in Chicago that sells Italian beef sandwiches, which is a very common item that you would eat in Chicago along with Chicago-style hot dogs. Okay, there's one chain of these restaurants which is called Portillo's here, and they're well known for, in addition to their Italian beef sandwich, their chocolate cake. Okay, so what we're going to do is create a systems chart for a chocolate cake. Okay, so what does that look like? So here is the processing structure property performance chart for this chocolate cake. So if I look down this column on the left, processing, it's very simple. There's a lot of mixing. That's basically the shake and bake that's happening. And then we bake, of course. Now, the structure, we can look at different length scales. We can look at porosity of the chocolate cake, the sponge. We can look at how homogeneous it is. And then we can look at the matrix. So it could have, chocolate chips in it, et cetera. There could be a secondary phase and so on. Now, for the physical properties of this chocolate cake that actually gives us the sort of satisfaction we have upon eating it, besides the flavor, is the response of the material, like when you bite it. So the viscoelastic response, we can measure this practice in lab. You can look at the cohesive strength of this material, and then also optically. You could define, what is a spectral range of interest that makes this piece of cake satisfying. And then the performance for this chocolate cake example, would you want to eat it, and is it aesthetically pleasing? So this is intended to be as simple as it sounds, but when we go to a real material system, it can become highly complex. So I just want to show you a few system charts of real material systems. So here's the systems chart of the C64 gear steel. So there's probably no metallurgist. I see Ichiro back there. He might recognize this gear steel. But you can see that it's quite complex. So in this case, you can process this material in many ways. The gear steel is hardened. The strength comes by various processing methods. There's alloying that happens in this. And then there's many physical properties that need to be satisfied ultimately to give the performance that the Air Force may want in its gear steel. Okay, so this is a metallurgical structural materials example. For this quantum materials workshop, I give you a systems chart for a superconducting qubit. So a traditional niobium or tantalum-based superconducting qubit system where you might have niobium resonators or LC circuits or tantalum LC circuits. And you can process, you know, a transmon qubit in many ways. There's many steps in the processing of a quantum computer and the chip. This will lead to structure changes, which lead to changes in physical properties, electrical, magnetic, thermal properties, of course, superconducting properties because they're superconducting qubits. And then this will affect the coherence times of the qubits. And so the losses that you have are often due to defects at the structural level. So you can have all of these links between the boxes, and this tells you, you know, what interactions or what interdependencies do you have on the way in which you process the material, the way in which you measure its structure, and how does that change the properties, ultimately performance you might want. So this is a highly complex diagram, and if you're creating experiments, you may want to isolate a few of these links, okay? So you might want to pull some out. Computationally, we can try to do that as well. You know, in the computer, we have almost the ideal experiment. We have complete control in practice of the boundary conditions, and we can put in defects or not. The question comes down, do we have a sufficient level of theory or model that will describe the system of interest? Another example is not a solid-state qubit, but here's a molecular qubit example. So here's a modified version of the systems chart, which has kind of been flipped on its side. Again, instead of solid-state systems, we might want to replicate molecular qubits for quantum sensing type applications. And here's another systems chart of interest. So this is an example of some system charts, and I'll show you one for the transition metal compounds that we're going to design for the metal insulator transition. So let's now talk about the model representation. And we've seen this actually throughout the winter school already, that the models have some external representation of some kind. Remember, the representation is going to be approximate, and it's going to be useful for some purpose, just like in the maps I showed you. You know, like the satellite image might be more useful than the image of just the transit map. And so here's an electronic structure model. So this is, you know, intuitive. We've seen this throughout. Here's the band structure. It's approximate. This is a density functional theory calculation. It's an approximate representation of the reality of that system, single particle electrons, and so on. We also have atomistic models. We've seen this many times. Many people have presented crystal structures. Here's a Lewis structure. We had nice versions of all of these this morning, and they're useful for different purposes. If I want to see different types of bonding, you know, I might have a representation which has a charge density. I want to see the electrons between the bonds, or so on. Then we have models which can be just simply equations, and then we have models which can be classification models as well. These might be machine learned representations. So now, these are the models we're going to use for this talk to design different quantum materials. And what I'm going to focus on is now this structure property part of the systems chart. Again, I'm not making things in the lab, so the processing is incredibly important, but I'm not going to focus on that here. And then ultimately the performance is important as well, but let's think about the structure property relationship. And so this is actually how I think about designing materials in my group, or how I try to teach students to design materials, and you can do what you want with it. But what I think about is what are the degrees of freedom available in a solid state inorganic material. It need not be inorganic, it could be a hybrid or organic material. And we want to ask questions about the symmetry. This is incredibly important, as we heard from Raphael's talk yesterday, the geometry and the lattice, the dimensionality, and I've been them in a few different categories. Are electron correlations relevant? What about magnetism, the orbitals that are filled? How important is spin-orbit coupling? What's the electronic band structure? What's the topology of that electronic band structure? We can ask something about quantum criticality, if that's relevant for the physical properties that we're trying to design. And maybe the last two things, which are also extremely important, but often very difficult to study computationally, is what is the role of disorder and defects? In some materials, it is the defects or the dopants that give rise to the physical properties, so we intentionally want them. And you know, what other perturbations are possible? We've been applying magnetic fields, electric fields. We heard a lot this morning about piezomagnetism. So there's a stress field. Is it homogeneous? Is it inhomogeneous? What type of response might I get? And when we're thinking about designing these, again, we're going to use atomistic models. So we're going to build up crystal structures where you want to think about the cation and anion composition. So do I have these types of metals or these types of main group anions? What's the composition, the ratio of cations to anions? What's the crystal structure? So how do those cations and anions tile to give rise to a periodic crystal? How do I perturb that crystal? Is it going to be, you know, a crystal or a material grown as a thin film? Will there be a strain field? Will it be a bulk crystal? Will I apply pressure to it or some light pulse? And then what about non-idealities? You know, there can be these interfaces, maybe intentional, a heterostructure, a superlattice, or unintentional. You simply have a surface. Is the surface oxidized? Is it that oxidized surface that gives rise to the properties? So it becomes very complex quickly. And when we're building up the crystal structures, we can use various units. And these are, I think, useful, as you'll see in the two examples, for understanding some quantum physical properties. So this transition metal, or this metal insulator transition compound, as well as ultramagnetism. And one of the ways we're going to do this type of design is by using this block of the main group anions up here, is by making chemical substitutions. Instead of chemical substitutions of cations, which happens very frequently, I'm going to make chemical substitutions of anions. Okay? And I've added something to the periodic table, which is above oxygen here, which is an oxygen vacancy. So oxygen vacancies happen naturally in materials. Thermodynamically, you'll have some concentration in a solid state material at a given temperature of oxygen vacancies. But there are compounds which can be described as ordered structural vacancies. So they are part of the structure. This is also a degree of freedom which you can use for the design of materials. None of the examples today, though, I'll tell you about, use oxygen vacancies. We'll simply use the anions on the periodic table. So for the example of a design of a metal insulator transition compound, this is going to be a material that undergoes a change in resistivity with temperature. We're going to be looking at the symmetry of the material, the geometry and the lattice, and maybe what the role of electron correlations are in driving that transition. So is it a Mott insulator? Is it a Slater insulator? Is it a Pyrrol's transition? What role do electron correlations play in this transition? And then for interest for this school, we're going to design an ultramagnet, or think about designing an ultramagnet. And as we heard yesterday, symmetry is incredibly important in whether or not we can have an ultramagnet. Sort of what's up here. All ultramagnets are antiferromagnets. And then we'll think about, beyond magnetism, what the role of spin-orbit coupling is. Again, this is a non-relativistic effect. And then we'll look at the electronic band structure and think about topology as well.
So it's a question about this. So why isn't band structure important for MIT compounds?
It is important. I just missed the check mark.
Or you're not making a statement saying that it's not that useful or something?
No. That's unintentional. Yeah, that's me not copying, pasting everywhere. Yeah. In principle, for all of these quantum materials, these are all active. The degrees of freedom are all active, of course. And when we're thinking about design, it's which one do we want to basically prioritize in the design. So, you know, for the electronic band structure, ultimately for this metal insulator compound, the question is, does it have a gap or not, right? And that, of course, is a band structure calculation, but we can also just count electrons, as Leslie showed us this morning. Yeah.
So a lot of these categories are very well defined.
Of course.
When I look at correlations or quantum criticality, obviously you need a model for how you're defining that, right?
Correct.
Yeah.
I will not talk about quantum criticality or even the correlations at any depth. So I've tried to make this very pedagogical without making this really a research talk, but yeah. Again, these are the principles, like when we're designing a material, we'll just sit down and sketch out what do we want to have active in our system, which one do we want to prioritize on the design. It may become even more transparent for the ultramagnets because the symmetry constraint is so strong that you can immediately start with that constraint, and then you can think about decorating lattices. I think someone had asked, like, how do you design, or maybe a friend was asking about the design of these materials. So if you have the constraints, you know the sites, you know where all the symmetry operations are in the unit cell, which maybe Karen will tell us about tomorrow. You can then design, these materials, I'd say rationally. Now the question is whether those materials are thermodynamically stable or metastable, and that's, we can, as a computational person, we can help you with that, but you have to go to the lab, and maybe we can prioritize, rank them, essentially, for you. Any other questions? So I'll maybe just pause here really quick. Okay, so we got through the first part. So this is the background. So hopefully you now know the difference between theories, models, simulations, if you didn't already. I tried to contrast forward and inverse design for you, so you should be able to do that. And then I've outlined the different degrees of freedom that we're going to study in these systems. So now I want to apply it to these two examples. And what we're going to do is come back to this diagram. Okay? So identifying the problem, we'll look at the inputs and outputs, what's the physical mechanisms, and then how do we interrogate the model. So the problem statement is very straightforward. I want to design a metal insulator transition compound. I want a material, single-phase material that undergoes a change in resistivity. Here's a thermally driven metal insulator transition, where upon cooling, we have metallic-like resistivity, so it's decreasing at a critical temperature. We have a phase transition, and then it exhibits insulating behavior upon further cooling. So this is the experimental resistivity of a well-known metal insulator compound, vanadium dioxide. So this is VO2. And what we want to do is basically make another version of vanadium dioxide. Okay? And we can sample, this diagram is not from the Ashby paper, this is my diagram. We can look at what existing single-phase thermally driven metal insulator transition compounds are out there. And those are all plotted on this diagram. So on the horizontal axis, we have the transition temperature for which this transition happens, the MIT happens, this metal insulator transition. So here's 350 Kelvin or so. That's vanadium dioxide, which is shown here. And then the length of this bar, or these various bars, tell you about the change in resistivity that happens from the metallic and insulating state. So how many decades changes in resistivity, and that's what's shown essentially on the vertical axis. This is relevant for particular embodiments of the system or memory devices, so they need to be of a certain order to basically beat CMOS type memory architectures. And so we want this bar to be as large as possible, and it needs to be a few more decades, at least for microelectronic applications, and we'd want it to be essentially above room temperature, around 400 Kelvin or so. So we want to design it somewhere up here. So what we can do is think about our design principles. Here's a systems chart for designing a metal insulator compound, which brings in another component of using AI or data-driven strategies. And I don't want to dwell on this too long, but what we're going to think about is composition. If I look at this box under the structure column, we want to think about new metal insulator compounds. So we need to think about what's the composition, what's the crystal structure, and what role magnetism might play. And then there are physical properties which we can compute, or if there are experiments being made, can be measured to tell us about the interdependencies on them. Okay? And then ultimately this will lead to performance metrics we can define as engineers. So what's the transition temperature, and what's that resistivity change that happens across the phase transition temperature? So we've identified the problem, straightforward. Now, in developing the model, what's going to be the input? So the input is straightforward. It's also crystal structure. So we're going to take the crystal structure and we want to compute the properties, or we'll have a crystal structure and we want to measure the physical properties. And again, because this is the ultramagnetism workshop, or novel and emergent magnetic phases, I've taken the rutile structure as a relevant phase of interest. So the rutile structure has an AB2 composition, and you can describe the structure kind of like we heard this morning for rock salts as a close-packed FCC structure. Rutile is derived from a cubic or a hexagonal close packing of anions. So these are the orange anions, and if we stack them in a close-packed plane, and we stack those close-packed planes in an ABAB fashion, we get the HCP structure. So those are anions, so that could be something like oxygen, sulfur, selenium, and so on. And then if we make those close-packed planes, we have voids in between. There are both tetrahedral and octahedral voids in between those close-packed planes. All of the octahedral voids are shown in black here. And now if I occupy those octahedral voids with cations, but in an alternating fashion, so I have a row here and a row here and like a row like that, and I alternate, and leave the other row vacant, those layers, I generate the rutile structure, which comprises metal ligand octahedra, which are edge shared and form infinite one-dimensional chains. And that's what this structure is here. Okay? So we heard about this structure, cobalt difluoride, manganese difluoride, and so on. So this is the crystal structure, and then I took a picture of Raphael's slides. So this is the rutile structure that he showed you. So this is my version of the rutile structure. But as he told you, this is a set of family, or forms a family of ultramagnet candidates, let's say. So ruthenium dioxide, manganese difluoride, and copper difluoride. So we're going to use the same crystal structure to design a metal insulator transition compound. And then the output, what we want is something like the electronic structure. So it does come back. So we're going to have the electronic structure. So here's the electronic density of states, or the band structure, so we can see the dispersion of states in momentum space. And what we're going to be looking for is that there's going to be a set of occupied states. Here we'll define the Fermi level as 0 in this density of states diagram. These states are all filled, and then we'll have a gap, and then the conduction band will be formed. These are the unoccupied states. So what we want to see is, as a function of some perturbation, there's going to be a change in a metallic or insulating state in our system. So these are the inputs, crystal structure. Output, we want some electronic property. And now let's talk about the mechanism. So of course, we're not the first people to look at metal insulator transition compounds. They've been studied for decades. And you can classify the types of mechanisms that are active in many, many ways. I've just shown one classification scheme here on this slide, where transitions are typically driven by instabilities of some sort. They can be valence instabilities, something like charge ordering that will lead to charge ordering. So nickel 3+ is somewhat unstable. It might want to be nickel 2+, nickel 4+. You can have orbital degeneracies. So manganese 3+ is Jahn-Teller, first order Jahn-Teller active. It has 4d electrons. It will lead to a Jahn-Teller distortion, a first order Jahn-Teller distortion. And this will change the local structure. It will change the extended structure. And then you can also have something like metal-metal bonding. Again, this would be a Peierls-like distortion. And these are active. This type of interaction is active dependent on the chemistry that you pick. So where on the periodic table you are, because you have to put electrons in orbitals, and those relevant orbitals will participate or provide for this interaction of interest. Now, those atoms are surrounded by, or those cations are surrounded by anions, so that gives rise to a polyhedral shape in an inorganic solid that needs to tile space, and that tiling of space will generate some known structure type, presumably, unless you discover a new phase. So here's that rutile structure again, and I'm showing you in this orientation the edge connectivity of the structure. So you have the one-dimensional chains this way. This, for example, is vanadium dioxide, where vanadium is the cation in the center of the octahedron, and then these red atoms are the oxygen atoms. So it's octahedrally coordinated. And now if I look at these vanadium atoms, and I draw this set of lines here, this basically looks like the one-dimensional chain model that Leslie, and we did not coordinate our talks, it just worked out this way, that you see for the Peierls transition, where she sketched going from atoms to molecules to bands, and you see this band degeneracy that might happen. So we have essentially D1 electron physics active with a one-dimensional chain, which is a materials representation of that simplified Peierls model that was shown earlier. So here's my version of that cartoon. This is that metal you would expect if all of these atoms are equally spaced. That's what you see in the active degree of freedom, this d orbital in this octahedral unit that goes along the z direction, the tetrahedral, or the tetragonal orientation of the structure. And now if you allow the chemical bonding, or that metal-metal bonding that we heard about earlier, this will open a gap at some periodicity, the atoms dimerize. And this is precisely what we want, right? This is the physics of vanadium dioxide. This is the physics of a metal insulator compound. So how do we realize this in a new quantum materials system? So we can look in more detail, if you like, at the orbital structure and nominally the high symmetry rutile structure. These are the active orbitals that are relevant. When we make the metal-metal bond, we form a bonding metal state and an anti-bonding metal state. This gets filled first, opens a gap, and then we have our insulated state. This is precisely what happens in vanadium dioxide. I don't want to dwell on this because I want to design a new material for you. The other sort of nuance that happens in this system, vanadium dioxide, is there's also sort of a rotation of the octahedral units. It's a rotation that follows the calcium chloride, dichloride type structure. So those occur together, and along with this first order phase transition, there is this symmetry break. So it goes from tetragonal all the way down to monoclinic, and you can use representation theory to describe that. You can see the splitting and the Wyckoff positions if you like. And this can all be measured experimentally. So now let's get to the model. So we have to construct the model with some level of precision, and then we have to implement it on a computer. And this I'm not going to tell you about. I'm just going to do it somewhat succinctly so we can focus more on the quantum properties of these materials, let's say. And there are many levels of accuracy or precision we might want. So density functional theory is widely used. There are, of course, beyond density functional methods. When you're constructing the model, you may be interested in equilibrium states or transport type properties. So you can perform also Monte Carlo simulations, molecular dynamics simulations. And as we've heard, there's also the now use of machine learning. This is the ML up here, which complements some of these more physics-based approaches, where it works in tandem or it supplements. In some cases, the DFT data is being used to train machine learning interatomic potentials, which then allow you to make a molecular dynamics simulation. So I have very schematically what's happening in density functional theory on this slide. Again, we take atomic representation, crystal structure, we solve some single particle Schrodinger equation formulated as an energy minimization problem. That's how it can be written up here. And this is essentially the workflow. If you haven't seen it before, you take a crystal structure and a composition, you solve for the ground state electronic wave function, you can compute a property of interest, and you analyze the results. And based on the approximation you're using, whether it's density functional theory or beyond, there are now mature electronic structure methods to do this part of the process for you. The bottleneck is still what is the structure that you want to study. And we heard this from a chemistry perspective this morning. And what we want to do is really build this structure property link here. So I'm trying to be mindful of time. So let's design the metal insulator compound so then I can get to the altermagnetism. And there's a subtlety which I didn't describe yet, is that when we choose chemistry, so we're going to use the rutile structure because we know it can host a metal insulator transition in it. Vanadium dioxide does that. But when we are trying to design for the transition, right, we're going from one state to another. That transition is driven by an instability. In this case, it's metal-metal bonding. And now when we design the material, if we are thinking about choosing chemistries which too strongly bias us in one direction, like the electrons always want to be delocalized, or we have too many of them, or the system always wants to have electrons localized, well, then we're going to be stuck in either the metallic state always or the insulating state always. So we won't have the transition. So phase transitions are this subtle balance of instabilities. If they're too strong, we don't get the transition, or it only transitions into one state, and the transition temperature is nominally very, very high, 1,000 Kelvin, which is interesting in physics, but may not be useful for the thing we're interested in. So to balance that, what we're going to think about is the electron count. We know it needs to be D1, because we want Peierls physics. If we look at the periodic table, we can get D1 electron counts in titanium 3+, as well as in molybdenum 5+, like that. We want the metal-metal bonding, so we're going to have the chain-like rutile structure. You could use other structures. And then we want some structural instability. And I didn't really discuss this critical tetragonal ratio, C/A ratio for the unit cell, but that's there. So what we're going to do is use the main group anions and this early set of transition metal elements to design these rutile structures. To get to these valences or oxidation states for titanium and molybdenum, what we're going to do is exchange oxygen for another anion, a different ligand. Okay? This will allow us to retain the D1 configuration, so we can do redox chemistry on the cation. And then what we're going to do is order the oxygen and the ligand anions, the subsequent other anions. And so when we are interrogating the model, these are the steps that we would go through. So we're going to look at the thermodynamic stability, the dynamical stability. We'll explore low energy polymorphs, and we'll examine the effect of site disorder. We heard about the important role of disorder. I'm going to mix two anions. The question is, will that be an alloy? So I have some equal concentration of those anions on all of the sites, or will it order? And that's a question we will need to ask in the design of these materials. We won't have time to go through all the details. Then what we can do is compute the electronic structure of those atomic structures with various levels of theory to understand the role of electron-electron interactions, magnetism, and so on. And then we can use more sophisticated techniques to estimate phase transition temperatures. But today, because we're winding down, we won't have time to do all of these things. The two examples I want to give you of how we, again, thought of these designs was we can take molybdenum dioxide, which is D2, mix it with molybdenum nitride, which is D0, and make this structure, molybdenum oxynitride, which is D1. Okay. The other version of this is to take titanium dioxide, a common insulator, semiconductor, and mix it with titanium difluoride, which is going from D0 to D1, and then we make titanium oxyfluoride. So these are two mixed anion compounds which have the nominal D1 electron configuration and adopt the rutile structure. Then we can go through the analysis that I just described on the previous slide. We can look at the atomic scale structure. We studied many, many polymorphs. And what we find is the structure is rutile, generally. It has two polymorphs. One polymorph, the beta phase, is the metallic one, which we call it. The other polymorph is the alpha phase, which is the insulating one. And the structure, again, has one-dimensional chains of octahedra. These octahedra have ordered anions around them. So they have oxygen and nitrogen in this FAC configuration. They're on opposite faces. In mixed anion materials, and there's a lot of materials chemistry that goes into it, this FAC configuration is the stable configuration for the local unit. And these materials do order with this geometry over some length scale. This system is being synthesized in thin film form. It's actually much more difficult to make this as a bulk single crystal. And over several nanometers, you can see this order. But beyond that, it disorders. Okay, so there's the length scale problem to that order. The other one is titanium oxyfluoride. It has essentially the same physics. It has a different configuration of the long-range oxygen-fluorine order compared to the oxygen-nitrogen order, but undergoes the same type of transition that I just described. And in this case, I'm just showing you the insulating case. This titanium oxyfluoride has been made by James Cumby's group at the University of Edinburgh, and they're studying the order in this system right now for us. So these materials have been made. So that takes me through that first example, and I've minimized all the details about interrogating those compounds, but you can go through the papers that were at the bottom there if you're interested in more information. So now let's design ultramagnetism. Again, sorry, Raphael, I took a picture of your slide. Yeah. So this is Raphael's slide. And what he told us about in terms of ultramagnetism is this spin splitting in the electronic band structure, so delta E at some position in momentum space. There's going to be a difference in the upspin and the downspin bands. And this is a non-relativistic effect. And the constraint, basically what will require or impose this symmetry, or this phenomenon, is that we have this rotational symmetry that will link the two spins together. Okay. And so for you, a homework assignment would be to create your own systems chart for the design of an ultramagnet. Interesting topic to discuss is really what goes in the performance part of that when you're talking about spintronic type devices. So we should discuss about that. Much of the discussion of ultramagnets has been on the identification and quantification of this delta E, but nothing really beyond that. And what this looks like atomistically, and this is a very similar interpretation that you see in Raphael's slides, is that if you have this translational operation that will connect these two sublattices, then you have a conventional antiferromagnet. But if you have a rotational operation with them, then you will have this spin splitting in the electronic band structure, and this would define our ultramagnetic type of material along with this classification. So when we're thinking about the physical mechanisms, let's go through our process again. So for the MIT compounds, I gave you types of interactions or instabilities that could be used to design a metal insulator compound. Now for an ultramagnet, what we want to think about for identifying the physical mechanism is something slightly different. So we can use a symmetry-based description. Okay, so group and representation theory. If we have magnetic symmetries, we talked about, or we heard about yesterday, time reversal symmetry combined with inversion symmetry. This won't allow us to have an ultramagnet. And then if we focus on spin symmetries, if we have the spin on two sublattices that are connected via translation, then we won't have the ultramagnets. So we have limiting conditions that allow us to think about how to design these. And again, for this ultramagnetism behavior, you have to have the spin reversal symmetry combined with a rotation of some type. It could be non-symmorphic, it can be a screw axis, etc. Okay. Another way, which I just want to introduce to you, is an approach that was developed by a postdoc in my group, Lindeng Yuan, who's applying for faculty positions, is to use spin structure motifs, which I think the materials chemists will like more than the symmetry arguments because it's a little bit more hands-on, let's say. And it's very fundamental to the description of the spin density of the system, which also Raphael was trying to reiterate many times, is you don't want to think about the spins as localized to a single site, but the spin density is distributed in space, and that has a structure to it. That structure was also identified in the original Rashba paper as a higher order term, and he referred to it as this inhomogeneous magnetic field in the material. So if you think about spin structure motifs, this is the idea. Instead of having the spin attached to a single site in the lattice, you want to think about the spin embedded within in some polyhedral environment, some local environment. In inorganic crystalline materials, this will be a metal coordinated by some ligands, okay? So you want to think about how not only this spin, but this unit is related to another unit in the unit cell with an opposite orientation in the spin. So if these units are interconvertible via a translation, then you don't have the spin degeneracy. Now, if you break that translational operation, then you have spin splitting in the electronic structure. And you can see very straightforwardly that this tetrahedral unit via translation cannot be interconverted to that other unit. So that black and white tetrahedron aren't interconvertible. So this can be applied to all of the known or previously identified ultramagnets, and the types of symmetries that they fulfill or don't fulfill are listed at the bottom. In a straightforward way, you can see now, again, this rutile structure. So instead of vanadium dioxide or ruthenium dioxide, this is nickel difluoride. You can see we break the UT symmetry, and this allows for ultramagnetism. This unit can't be translated to that unit because of the connectivity of these units, which is via a 2-1 screw axis in the rutile structure. The other advantage, maybe, or sort of useful insight that can be obtained from this structural perspective is understanding the band dispersion in momentum space, which I highlight with this cylinder if viewed along different axes. If you view it along this x-axis, it looks like a circle in projection. If you look along the y-axis, it essentially looks like a square. But both are true, right? This is the true representation of the system. Now, if you take rutile, and I just slide it over here, and you look along the different directions, you can see that these two units in projection are translatable on top of each other. And in this direction in momentum space, there is no spin splitting. Now, if you look along another direction, you find that the two units are not interconvertible in the two-dimensional projection, which is this cut that you're taking in momentum space. And there, then, you have to have the spin splitting. So this ability to connect between the structural motif, recognizing that the spin density spills out onto the ligands, again, is useful in thinking about this spin splitting. So I just have a few minutes left. Let me tell you, what happens if we lift this rotational symmetry. And this is, again, the design of an ultramagnet type of material, and we recently reported this. So this is the ultramagnetism that we've been hearing about. So these two units are related via a rotational operation, and this is schematically what you would get in momentum space via this rotational operation. And now if we lift this rotational operation, what we find is that you can lift the degeneracy that's protected at the gamma point in the crystal. And in fact, it shifts it to another high symmetry point in momentum space. The details of that I won't have time to tell you about. But what we were looking at to realize this in experiment is a new material family. So these are the transition metal nitrides. This is the compound manganese silicon nitride, which is essentially a Wurtzite-like structure where manganese and silicon are ordered. Manganese is 2+, so it's a D5 electron system, and this material has been synthesized in collaboration with Stephen Wilson and Ram Shishadri at UCSB, and they made this material, and we were interested in studying it. Well, one, it's an interesting antiferromagnet that orders above room temperature, and so we were interested, is this an ultramagnetic compound? And the answer is not really. So if you look at the band structure, and this is the, on the far left, this is our atomic representation that I was describing to you. We have two different tetrahedra in this unit, so we have manganese up and manganese down. These are related via symmetry operations that I show you on the bottom here. These are rotational operations or improper operations, glides and screw axes. These operations protect the spin splitting, so there is no spin splitting essentially everywhere in momentum space except this line gamma to r. Okay. So maybe not that useful. But what we realized, and what's known, in fact, is that experimentally, this is a family of compounds. So manganese silicon nitride, if you go down this group 4, there's actually a manganese germanium nitride, and there's also a manganese tin nitride. Those have all been synthesized experimentally. As you go down, not surprisingly, the band gap gets smaller and smaller, so it goes from an insulator to a semiconductor. But you can realize essentially all of the same magnetism. So what we were interested in was a cation-ordered version of manganese silicon nitride, where what we did is we substituted half of the silicon sites, like this, with tin. So they're of large enough ionic size difference that they should order, and we studied computationally, various configurations. We also looked at the disordered version, and what we found is that the lowest energy structure for this compound, manganese silicon tin nitride, in fact, is this wurtzite kesterite structure, a known ordered wurtzite structure. And if you look at this compound, this material, because we've lifted the rotational symmetries that protect the ultramagnetism, or in fact, the translational symmetries that protect the ultramagnetism, we get this giant spin splitting that happens at the gamma point. And it shifts the degeneracy that's protected to the C point in momentum space. So this is an interesting way, again, to think about how to design for different types of phenomena, again, spin splitting in this case, and this is something a little bit beyond an ultramagnetism, because we've lifted, in fact, the rotational symmetries. So we've added another designation, for better or worse, to this community, in the sense that we have something that doesn't have spin splitting, to something that does, and it's an ultramagnet where this rotational symmetry protects it, to one that has this non-relativistic spin splitting, but the gamma point degeneracy is lifted, and you can think of another version of that where it's even adopted or changed even further. And the idea is you can use, again, these spin structure motifs to generate types of patterns. And now the trick is computationally, to find relevant compounds for experimental synthesis, and my job is to help prioritize those, so you actually spend your time on something useful. And so I recognize, and we'll hear more about this tomorrow, that this magnetic symmetry analysis is not simple. And that's true. So what we've done to try to help experimentalists, and we haven't automated anything here, but you can imagine automating something, is we created this small utility for you, which is called FindMagSim. And if you're an experimentalist and you have the MSIF, the Magnetic Crystallographic Information File, you can upload it on our website, and there's two examples there for you. There's magnesium difluoride and this manganese silicon nitride example that I just described to you. Those are there for you. And it will give you the magnetic space group symmetry with and without spin orbit coupling for you. And it will also classify the compound. So it will tell you if it's an ultramagnet or not using our own sort of designation scheme here. And the information to do this is available on the website. Currently, it only works for collinear magnetisms. The non-collinear version is essentially there. We're just debugging it, but that will be available soon. And if you have the magnetic structure, you solve the magnetic structure doing neutron diffraction, you can check very quickly. It takes less than a second to run whether or not your system is an ultramagnetic system. So that essentially takes me to the end of developing forward and inverse models. I just want to thank you for your attention. This is my research group. Again, we have a beach in Chicago. You're welcome to come join us. And I thank you for your attention. If you have any interest in our work, again, you can scan the QR code. So that's it.
Thank you very much. Great. Questions?
Oh, all the way.
Yeah.
Yeah.
So, thanks, James. Just going back a few slides where you were sharing sort of the real space perspective, sort of the project, yeah, this one. you comment a little bit more on that? So something I've been trying to sort of think about is how does one predict the direction of, in the band structure and momentum space that the splitting is supposed to, in a system like this, and alternates should arise on, based on the real space.
Yeah, like this picture.
Right, based on that, and the Neil vector and so on. Can you maybe touch on that a little bit more?
Yes.
A simple way of thinking about that.
So the way we've been thinking about it, and the details are in this paper here. Again, if you take and look along the 100 direction, which will define the 100 plane like that, you have a translational operation that will map those two in the same plane, and then they're protected. Now, in the other projection, the 110, this is not the case. And essentially that's it. It won't tell you any more about magnitude, the spin splitting. And I think we heard maybe a little bit, I guess you missed, but understanding what drives the magnitude is incredibly important. It seems in the perovskites that have been studied, the degree of octahedral tilting, which changes basically how much the spins delocalize on the site, will affect the magnitude of that. So I think thinking about the spin density distributed in momentum space is probably the way to think about amplitude. But then if it's present or not is essentially this schematic of can I apply the spin operation plus translation to map the units on top of each other.
Any student questions first?
Yeah.
In your the example, so in your input, you had a resource structure that is pretty well studied and well known that structure. But in general, like for any problem, we might not know like what crystal structure.
Yeah.
And so and there are all these like crystal structure prediction algorithms available now, right? And there are also some machine learned structures papers that have come. What do you have comments on, like how good they are, or like
Yeah. So the question I think was, in the presentation I gave, I was making substitutions like a chemist would, and I think that's fair. And that's actually a large part of what my group does, is to identify known structure types and look for new compositions in known structure types. The question pertains to like the discovery, sort of really new structure types, which I think is incredibly difficult for binary compounds, still difficult for ternaries, but the phase space that's open is, quaternary compounds. But then we have Pauline's rule of parsimony, which tells us, it's going to probably adopt a simpler structure or be two-phase. So there are generative type algorithms, both physics-based, where you can do like mutations and you can cut crystals together, put them together, assemble, which will allow you to sample new structure spaces, as well as sort of machine learning models. We've seen, you saw the DeepMind report, which gives you something, but it's not real, perhaps, for a lot of things. So I think, for a graduate student who has a time scale of 5 years, you should probably largely focus on known compounds or phase spaces which have been sampled but are not complete, I would say. And then try 1 or 2 high-risk explorations for really new phase discovery, because that is incredibly challenging. I mean, that's still a forefront problem in materials research. So yeah, I guess that would be my comment.
Yes, then Raphael.
I'm wondering how you're able, in your fine accident program, how you're able to screen like rotational symmetries that are dependent on sort of the surrounding space, like matrix operations. So, you're talking about how these magnetic dipoles, you have to consider sort of the volume around sort of the local environment in certain octahedral spaces. I'm just sort of wondering how you represent that in math.
Yeah, so this physical interpretation is consistent with this magnetic symmetry analysis. In the magnetic symmetry analysis, what's done is essentially all of the occupied Wyckoff sites are known, and this representation of the unit, like the polyhedral unit, is captured by the metal surrounded by some ligand environment. So how the ligands map onto each other is also evaluated in that algorithm. Yeah. It's nothing new, like that program at the end is in many, many papers. We simply just put it online, and I think many groups have their own version of it. They just haven't made it available, like that symmetry analysis. It doesn't use anything we created. We've just basically, what is it? It's, there's a crystallographic symmetry finding utility and there's a magnetic symmetry finding utility, and we basically just combined the two of them together and then added the post-processing vector analysis, but that's it.
Okay, Raphael.
And then I stand between you and lunch, so just FYI, you're getting close.
Two quick questions, Raphael, very quick.
Yeah. Okay, that's good. Okay. Yeah.
Thank you so much for the nice presentation. So I'm wondering that can you elaborate on the fact that why CuMnAs is not an alt-magnet while being a polykinetic magnet?
Maybe. Which one was in my full table?
First one.
This one, copper manganese?
Yes, the first one.
Because it has both, it has this time reversal, and it has an inversion operation. It has parity there. In between the sites, yeah.
I see. So that means like universal symmetry is not, right? It's preserved.
There's an inversion here.
Thank you.
Raphael?
So, very nice talk. I was, I'm thinking about how to, it's very nice that you can do everything in this systematic and intentional way. But at the same time, how much our reliance on the methods that we have can limit us? Let me give you an example, like ruthenium oxide, right, that I mentioned. So people did first principles, and then they said, well, we have to do P plus U. If you do U1 EV,
Yeah.
it's not, but 1.5 is. And then you start arguments with like, well, 1.5 is much larger than 1, it's ridiculous large. And we start, going to methods that we know don't capture, and then we try an approximation and we start overreading them. It's not a criticism of the method, it is what we have in hand, but how much do we need to improve methods or rely on multiple methods maybe to constrain, to view things?
Yeah, I think it's the latter, it's the multiple methods. It's similar to what we heard about the crystal structure identification. You have to do X-ray diffraction. You also have to identify the chemical composition. There's multiple things that need to be consistent. I think that's probably the approach we take as more sophisticated, then only a single metric might be evaluated. But again, coming to ultramagnetism, I think beyond thinking about just the band splitting, and this is maybe more common in the materials community, we should think about other screening metrics to decide on what to pursue experimentally. So, if the material is highly defect sensitive, like you have anti-site defects that happen spontaneously, or there's a large concentration of oxygen vacancies in the material, we're gonna shift the chemical potential. Like, should we put a bound on what reasonable defect formation energies are in a material that's an ultramagnet before we invest time in working on single crystal synthesis? Because it may be the best candidate, but it may take a lot of time to process that material to the fidelity you want. And that's in my community, that's what we like to think about, is those other important aspects, in addition to the fundamental physics. And again, they have to work somewhat hand in hand, because we want to make progress, and then evaluating them, I think you want multiple schemes. But I'm happy to answer any more questions at lunch. I'll join you all for lunch.
Yeah, you mentioned the key word, which is lunch.
Okay.
Thanks, James.
Yeah, you're welcome.